sequence messed up. All right. So again, in chapter 7, we have to do 7.2 first, because there's some stuff that I ask you to do on there that you need information from 7.2 to do. So we're just going to put a pin in that for a minute. We're going to do 7.2, and then we'll do the activity. Okie dokes. All right. So in chapter 7, we've been talking about descriptive statistics. So today we're going to be looking at ways to kind of display your data. So again, we've talked about qualitative variables that basically place individuals into several groups or categories. One way to kind of display that data is with something called a frequency table. So on the left here, you see these are the qualitative categories. So this is like music preference. And then this would be like the number of individuals that responded to that being their preference. And you can have a frequency table or a relative frequency table. Here we've represented the frequencies as percentages. Notice that if we add these percentages up, we don't get to exactly 100. Why do you think that happened? Rounding. Good. You should have said it louder and everyone would have been really impressed. Yeah, so there's just a rounding situation where it didn't get to exactly 100%. Okay, so again, when we write our frequency table, we have our variables here. That's the format, and then the values are the individual different formats, and then the counts or percentages. It's so fancy. Okay, so again, we want to talk about discrete versus continuous. These frequency tables can be sometimes difficult to kind of see what the pattern is going on. So when we have a discrete data like this, where again, either this is your preference or it's not, it can't be like, well, it's like 50% of my preference is this and like 38% is that, like you can't say that. You just have to pick one. But to take a discrete data like this, it's oftentimes you get more of an impression of what's going on by displaying this data as some kind of graph, like a pie chart or a bar graph or whatever. So let's say we take this relative frequency table and we turn it into, that's not the relative frequency table, that's just the frequencies, and we turn it into a bar graph. Right? We look and we can see that what's the most popular? Yeah, the news, which is surprising or whatever. And if I want to take the relative frequency table here, since I know that the total sum needs to be about 100, it makes much more sense to take that and make it a bar graph, where again, we can see that the biggest wedge of our bar graph is this news. You want to make a killer radio station, it appears that like doing news and country would be the way to go. Whoa. Everybody okay with kind of what we did here? So bar graph, again, your different qualitative values are your labels on the x-axis and your y-axis is your count. Okay, let's talk about kind of how to do this, constructing these kind of graphs. So bar graphs compare several quantities by comparing the heights of the bars that represent those quantities. Our eyes, however, react to the area of the bar as well as their height. So when you're making your bar graph, you want to make your bars equally wide, right? You don't want to make like a big fatty bar and then a bunch of little skinny ones. That's bad graphing. And sometimes it's tempting to like replace the bars with pictures for greater eye appeal. If you looked in on like a magazine before, they might have something about schools, and instead of bars, they have like little apples stacked up or something to make it cute. Don't do that. So the two important lessons to kind of keep in mind, beware of using a pictograph, using pictures instead of a bar, and then to make sure you're paying attention to your scales, that you want your bars kind of equal widths. So you saw at the beginning, we showed you those two-way tables where we had the qualitative value and then the count next to it. So a two-way table is a great way of kind of displaying your raw data collected. So usually in a two-way table, you have like a variable for your row and a variable for your column. Oops. So here our column variable is the, these answers to this question. The chance that young adults get rich. And then the row variable is going to be male versus female, right? So if we wanted like how many total young adults are surveyed here, yeah, 4,826, which is our total of the totals, right? And then, again, the individuals that are described in this table are young adults, and the variables would be gender and then your response to your chance of getting rich. At times, using grouped data allows us to see general patterns more clearly despite the loss of details. When we do the statistics in our IA, we'll be doing some grouping of data to do that. So to group discrete data, you want to find the highest and lowest value across your frequency table, and then rearrange your data into larger groups of equal ranges, not necessarily size. This means that if you have one group of numbers from 10 to 15, you should not have another group with the numbers 15 to 30. Why not? They're unequal sizes, right? Unequal ranges, right? One is covering just 5 values. This one is covering 15 values. And then we count the number of individuals in each group. And then again, sometimes when you're doing this grouping, percentages can be more helpful than just a raw count. Just kind of depends on the situation. So let's say we have this situation where Ryan records the number of tardies each of the 20 students in his class has over the course of the semester. So here is his results. Notice there's 20 numbers listed here. So we might make the groupings of 0 to 2, 3 to 5, 6 to 8, 9 to 11. And if we fill that in, we see that there's 8 individuals that had 0 to 2 tardies, right? 1, 2, 3, 4, 5, 6, 7, 8, etc. And the total should be the 20 students in the class. We might also represent that with a relative frequency using a percentage. So 8 out of 20 is 40%, 4 out of 20 is 20%, 6 out of 20 is 30%, etc. Notice here that all the relative frequencies added up to 100 because we didn't have to do any rounding here. Everybody feel okay on how we constructed a relative frequency? Because you're going to do this in a second in the activity. Okay. So if we have continuous data, again, we still may want to group this kind of into distinct categories. And effectively what this does is it translates our continuous data into discrete data. So again, to do this, we find our highest and lowest values across the frequency table, rearrange our data into larger groups of equal ranges, not necessarily sizes, decide the method for your boundaries, and then again, your equal ranges, if you have 10 to 15, you shouldn't have 15 to 30 because this contains, a range of 5 and this one has a range of 15. And then we count the number of individuals in each group. So when we say boundaries, that's like 15 would be a boundary between the two groups, right? That's what we mean by a boundary. Is there a set way in which we have to do this? No, not really. There's not one single way to do this. Particularly if you have continuous data, you could pick 15.1 as a boundary, or 15.02, or 15.7, right? Like, if it's discrete data, it makes no sense. You have finitely many choices for your boundaries, but with continuous data, there's infinitely many choices. So that's also something to kind of keep in mind. And again, like using a relative frequency rather than a raw count, again, can be helpful. So, when I say class here, what I mean is all of the groupings taken together are the classes. So that's when I say class here on the next page, that's what I'm saying. So let's look at some different ways of kind of setting up these boundaries. So suppose you record the heights of plants ranging from 2.8 centimeters tall to 28.6 centimeters tall. Remember, height is a continuous variable because you're going to have something that's 1/10 of a centimeter, 1/100th of a centimeter, 1,000th of a centimeter, just depending on how good your ruler is. So you might set them then 0 to 5 and then 5 to 10. Notice where the inequality symbol is here, right? We're always going to include at the lower bound but exclude at the upper bound because you can't include 5 here and here. You need to be careful on how you're setting your boundary there, but that is one way we might do that. And here's some made-up frequencies and some made-up relative frequencies based on those. So if I had a plant that's exactly 15 centimeters tall, which group would it go into?
15 is less than.
Yeah, the fourth one, right? If it was exactly 15, it would have to slot in here. All right. So if I have discrete data, and I'm using a discrete situation, so recorded the weights of players at a soccer game, here, apparently the way we're doing this is we're always going to be rounding to the nearest kilogram. So our data's been discretified by the way we've done our measurement. So here I have 61 to 65, and then I go 65 to 70. Notice that I can tell immediately that it's discrete because there's no place for like 65.1 or 65.2 or 65.5 to be represented anywhere in this table, right? So again, there's my discrete, and my made up some frequencies and then calculated some relative frequencies based on that. Now, again, really important that when you're looking at these two-way tables, that you're reading the boundaries very carefully. So take a look at these two situations. What's the difference between the two? The top grouping would include 0 but not 5. The bottom grouping would include 5 but not 0. So again, making sure that you're being very careful about kind of how you're writing your boundaries out, that you don't leave any ambiguity, don't leave anything uncovered, particularly for continuous. So let's look at things that we can do with group data versus individual data. So one of the issues with group data is that we're taking extremely detailed individual data and making it more general by combining the data into groups. This allows us to interpret the data by identifying overall patterns. However, it makes the data more inaccurate and harder to come up with specific information. In order to reverse this process, to take our group data, or take the group data that you don't know the individual data for and try to extract individual data from it, we could look at the original data from the population, but if we're only given the frequency table and we have no access to the actual data that the person collected, that is impossible to do. However, to make meaningful calculations from a frequency table without having the raw data, we can use something called a mid-interval value. This is the value exactly halfway between the upper and lower boundary of a particular class or group. So if I look at this first grouping, what would the mid-interval value be here? Halfway between 0 and 5 is 2.5, right? Halfway between 10 or 5 and 10 is 7.5, etc., right? So here's me calculating the mid-interval values. You get the idea here. Mr. Kulik, this is so complicated. No, it's not. So again, what am I really doing here? I'm taking the average of the upper and lower bound, right? Okay. What if we do this one? What kind of data do we have here? Discrete. So when I look at the lower boundary here, what is really the lower boundary? It's not 61. What is it really? 60.5. And what's the upper here? Not actually 65, 65.5. You can think of it as 5, and we're just deal with the inequalities and where to put it. So when I do this, I'm really getting a mid-interval value of 63 here, as opposed to using 61 and 66. Now, you might say, I still get 63 when I do that. We're being technical here. So what does this mid-interval value allow us to do, right? Remember, we got into this by talking about how do I extract individual information out of a frequency table, right? Out of this grouped data. So what we can do is we can treat those mid-interval values as the actual value for the individual in that particular class. While this is not obviously true, right? If the people responding between like 61 and 66, really everybody in there isn't a 60 or 61 and yeah. What was it? 61 and 66 was the last, or 61 to 65. Everyone in there doesn't weigh 63 kilograms, but it allows us to like approximate what the total weight of the individuals in that category would likely be. So this is going to allow us to find things like mean and median and standard deviation. And it'll always, everybody's okay with that? So if I wanted to do go back here. If I wanted to do the mean for this data set, I would do like 63 times 8 plus 68 times 15 plus, and then divide all that by 66, would give me the average or mean weight of an individual in this data set. Is everybody okay with that? Or if I wanted to find the median value, I could line them all up on a number line and find the middle value, or the average of two middle values, since it's an even number of individuals. So we said that. Okay, another way to display these variables is with something called a histogram. So the most common graph of the distribution of one quantitative variable is using a histogram. So to make a histogram, we're going to divide the range of data into classes of equal width, find the count or percentage of the individuals in each class, and then label and scale the axes and draw the histogram. The height of the bar equals its frequency. Adjacent bars should touch. That is, unless a class or grouping contains no individuals. So difference between a bar graph and a histogram. Histogram, the bars touch. The bar graph do not. So let's take a look at, say we have this grouped data. So we have 0 to less than 5, 5 to less than 10, 10 to less than 15, etc. 50 total individuals. The counts are right next to them. If I build my histogram, here is my x-axis. So the table was the percent of residents from each state who were born outside of the United States. So my x-axis is going to be percent of foreign-born residents, going from 0 to 30. So 0 to 5, the count is 20. So I'm going to build a bar that goes from 0 to 5. And then 5 to 10 is 13. So from 5 to 10, I'm going to build a bar with height 13. Notice that all the bars are touching because all the groupings have at least one individual in them. Everybody's cool? Okay. Notice that when I drew my histogram, I didn't decide on the ranges, right? Those came directly from the frequency table. I'm just taking what's in the frequency table and converting it into a graphical representation. Keep in mind when you're doing this, notice that both my axes have labels, right? I've told you what the X and Y axes are labeled. When you draw your own bar graph, histogram, whatever, things need to be labeled. Everybody's cool? Okay. So common mistakes when you're making your histogram. So be careful. Don't confuse a histogram and a bar graph. They are different. What's the major difference? Histogram, the bars touch, right? The x-axis of your histogram is going to be numeric, right? A bar graph, the x-axis could be qualitative. Everybody's okay with that? So we don't use counts in the frequency table or percentages in the relative frequency data or table as data. But we use percentage instead of counts on the vertical axis when comparing distributions with different number of observations. So if we have two different situations where it's like, like we had the number of, if we go back here, say we had this for states and we did the same thing for like provinces in Canada or something. There the variables are different. So there's a different number of provinces than there are states. So looking at a relative percentage would be more informative there than actual counts. And just because a graph looks nice, it's not necessarily a meaningful display of data. Another way we can display data is with something called a dot plot. So this is maybe the simplest of all graphs to construct, where above each value, we write a dot every time that value occurs in our data set. So again, we draw just a horizontal axis like a number line and label it with a variable name and scale the axis from the minimum to maximum values in our data set, and then mark a dot above the location on the horizontal axis corresponding to each data value. So here we have collected the number of goals scored per game by the 2012 U.S. women's soccer team. So our smallest value is 0, our biggest value is 14, so those will be the bounds on my dot plot. And every time I have like a 0 occur, I put a dot. Every time 1 occurs, I put a dot. So notice there's 4 dots above the 1 because I have 1, 2, 3, 4 ones. Is everybody okay with that? Oh boy, it's hard. The biggest problem is people forget to label their axis. So when we build a graph, the reason we're doing this is to help us understand the data. So once we've constructed this graph, the question is now, like, what do I see and what does that tell me? So in any graph, we want to look for an overall pattern or striking departures from that pattern. And then what we'd want to do is describe that overall pattern by its shape, center, and spread. Those are 3 common things that we'll always use to describe the distribution that we've graphed. And we call the individual values that fall far outside the overall pattern outliers. And we'll talk about what we mean by shape, center, and spread here in a moment. I'll use the acronym SOCS for shape, outlier, center, spread. Like that'll be something I use frequently because those are things, yep, there it is. Those are things we want to talk about when you interpret your graph. All right, so let's talk about shape. When you describe a distribution shape, you concentrate on the main features. You look for rough symmetry and clear skewness. So what do we mean by symmetry? We say a distribution is roughly symmetric if the right and left sides of the graph are approximately a mirror image of each other. A distribution is skewed to the right if the right side of the graph, containing half of the observations with larger values, is much longer than the left side. We say it's skewed to the left if the left side of the graph is much longer than the right side. So if I look at this one, where would we say the center of our graph is? Kind of like right in here-ish, right? Everybody agree? To me, this looks pretty symmetric because it looks like we have about the same amount of stuff on each side of that. If I look at this one, the center of my graph looks like maybe it's about here. Here, the right side has a much longer tail than the left side does. So I'd say that's skewed right. If I look at this one, the center of my graph is maybe here. There, the left side is much longer than the right side. So we'd say that's skewed left. Everybody okay with that idea? So, do you guys remember what mode is from, I don't know, pre-algebra probably? Yeah, mean, median, and mode. Which one was mode? The most frequently occurring, right? So a lot of data is going to be unimodal, so it would have just like one peak, right? So this data set here of dice rolls is unimodal, as is this with siblings, or this one with scores. But, can we have more than one mode? Sure. Yeah. If, like if I lopped, those 3 values or 4 values off there so that we had the same number in each peak, that would be bimodal because there would be 2 modes. Everybody okay with that? If I lopped, some of these off so that I had 3 that were the same height, you could call it trimodal or just multimodal in general. But that mode is kind of taking or representing our center more often than not. Okay. So again, when comparing 2 distributions, we're always going to be discussing shape, center, spread, and possible outliers. So here we're looking at the size of your average household. So that means like the number of individuals living together, and comparing that between South Africa and the United Kingdom. So if I look at South Africa here on top, what would we say the shape is?
Skewed to the right.
Skewed to the right. I mean, the center looks like around here, and certainly they've got a big long tail to the right. Outliers in South Africa? 26 and maybe 15, but definitely 26, right? The center? Well, it's a count, right? You're trying to find like the halfway point, so there's an equal number of data on each side. So I'd probably round here between like 5 and 7, right? Everybody agree with that? And then the range would be is our proxy for spread. So our smallest value is 3, our biggest value is 26. So it looks like the range would be 23. That would be our spread. Now to compare that to the United Kingdom, what we say the shape is here. I would say it's roughly symmetric, yeah. Are there any outliers? No, man. The center is probably here between 4 and 5. And the range, what's this going from? Like, I don't know, 2 to 6 or something? So if we're to compare these two, we saw that the centers were reasonably close. They're both kind of, this was 5 to 7. This was like 4 or 5. That's pretty close. The shapes are different because this one is skewed right and this one is symmetric. This is certainly way more spread out, going from 3 to 26 versus 3 to 6. And the result, and a large part of that is the outlier here at definitely 26, where UK has no outlier. So if you ask for like a comparison between the two graphs, that's the kind of discussion you'd want to have. Like, oh, their centers are similar, but they're, the shape is not, and the spread is way different. And because this one has this clear outlier and this one has no outliers. That's the kind of discussion that you'd want to make. So you're going to actually have to write words in complete sentences. I know. All right. More ways to represent data. So one other way is with a stem and leaf plot, or just a stem plot, I think is the way that the IB uses their vocabulary. So again, what the stem plot does is it gives us a quick picture of the distribution, and it includes the actual numerical values. So what we do to make a stem plot is we separate each observation into a stem, that's everything but the final digit, and a leaf, that's the last digit. And then we write all the possible stems, starting from the smallest to the largest, in a vertical column, and draw a vertical line to the right of the column. And then we write each leaf in the row to the right of the column, and we arrange those leaves in increasing order out from the stem, and provide a key that explains in context what the stems and leaves represent. So let's look at an example here. So this is the 20 responses of the responses of 20 female AP statistics students on the question, how many pairs of shoes do you have? So if I look at my values, everything is kind of between, 0 and 100, right? But everybody has double-digit shoes. So my stems are going to be the tens places. So I would start with 1 to 5 or 1 to 5. Okay with that? And then the leafs are going to be the digits in the ones place. So under 5, I'd have a 0, I'd have another 0, I'd have the 1, and then I'd have a 7, because I have to write them in order from smallest to largest as I'm moving away from the stem. Okay, so here I guess I did it just as I read through the table, but here then I ordered them. And this should be your stem plot, but it's still missing one thing. What is it missing?
Labels?
Well, it's missing the key to tell us what these numbers mean. So what would I write as a key? Number of shoes owned by female AP statistics students. So I write, for example, 4/9 represents a female student who reported having 49 pairs of shoes. Most common mistake students make on this is either forgetting to order their leaves, and then most common is they forget to write a key. Oh, those easy points that you lose for just being forgetful. Okay. All right. When data values are bunched up, we can get a better picture of the distribution by splitting stems. So two distributions of the same quantitative variable can be compared using a back-to-back stem plot with common stems. So for example, let's say we have some data that's both male and female. So I'm going to do, I notice that my values run from single digits up to the 50s. So I'm going to do 0 in my 10 spot, and that'll go for the single digit pieces. And then all the way up to 5. And I'm including double stems. So for the double stems, I'm going to have the stuff that's like 0 to 5 on the first stem and the stuff that's 5 and above on the second stem. So I did this for males. And then what I'll do is I'll draw a second vertical bar, and on the other side that I'll label as females, I'll do the same thing for females. Everybody's okay there? What have I not done yet, though? I need a key. So 4/9 represents a student who reported having 49 pairs of shoes. Notice what word did I drop here? Female, because now my data is both male and female. It's not a single gender. If I asked you to compare these, what would we say? Let's do the socks for these. What appears to be the center for the males? Well, remember, this is like 5, 6, 7, 8, 9, 10, 10, 10, 10, 10, right? So the range there, or the center there, appears to be somewhere around like 8 or 9, 7 or 8, something like that. Appears to kind of be where the center is. Everybody agree? And then what we say the shape is? Skewed to the right. Remember, this is right because these values are getting bigger. Everybody's okay there? Any outliers? The 35 and 38 appear to be outliers, sure. And my range there appears to be 4 to 38, so 34 would be the range, right? How about for the females? Where's the center there appear to be? I don't know, I'd probably guess right around here somewhere. I think there's probably about an equal number of numbers there as there, without counting. So probably in the 20s. So that's already a much higher center, right? And then as far as the shape goes, what we say here? I'd still say skewed right. That's a much longer tail. But I'm not sure I would say there's any outliers, right? This seems to be pretty consistently tailed that way. And my range still goes then from 13 to 57, so whatever, 44? That's math is hard, guys. Okay. Certainly. All right, so one thing that we're going to be of particular interest to us, and we'll build on this idea in future chapters, is kind of measuring the position of a value in its distribution. That position is something we call a percentile. So we say the pth percentile of a distribution is the value with p% of the observations less than it. Do you guys know of anything that you get that's represented with percentiles? Well, certainly the PSAT is, like the ACT raw score is not a percentile, but I think they probably give you percentile ranks in there also. It's been a long time since I've looked at ACT. I was thinking the PSAT, where your score is just simply a percentile, right? Like, I was 86% for English and 92% for math or whatever. right? That's how they report those. Okay, so let's look at an example and calculate a percentile. Jenny earned a score of 86% on her test. How did she perform relative to the rest of the class? Well, I see that Jenny's score was greater than all of these ones in red. So if I count those up, there's 21 numbers there. And if I count up the total, there's 25 people in the class. So since 21 out of the 25 were below us, we were the 84th percentile in the class. Is everybody okay with how to do that? Can you ever have the 100th percentile? No, why not?
Not 100% people. 100% of people below you.
Right, because
Oh,
of you, right? Because you don't count yourself. So you can never be 100th percentile. Good job. Okay? So another important concept is this cumulative relative frequency graph. So this is a similar idea of the percentage. So here's our two-way table. Here we have the age of the U.S. president when they are inaugurated. This is probably not complete because looking here, I don't see any super geezers for our last couple of presidents. And then the frequency in which that a president occurred with that age range. I'll convert these into relative frequencies. And then if I want a cumulative frequency, so here is just 2. And the next spot is 9. How did I get the 9? 7 plus 2. And then I have 22. How did I get 22? 13 plus 7 plus 2. Everybody gets this? Okay. What should the last number in your cumulative frequency table be? The total. Yep. And now if I want the cumulative relative frequency, I'm going to do 2 out of 44, and then 9 out of 44, 22 out of 44, and then the last one is 44 out of 44. The last value in your cumulative relative frequency should always be 100%. Is everybody okay with how we did that? Again, what's going to be the hard part here? Keeping all the names straight, right? Like the actual calculations here are very algebra 1 or sub-algebra 1 calculations. But remembering like, oh, what do I do for frequency, relative frequency, cumulative relative frequency, like keeping all that vocab straight can be a hassle. So if I wanted to plot my cumulative relative frequency graph, it would look like this. So how did I draw this? Well, I used the lowest end of my range, and then I plotted like 40 and then the 4.5%, and then I did 45 and the lowest end of my range was the 0, right? Because sub 40 is 0. And then at 44, I plotted the 4.5. And then at 49, I plotted the 20.5, etc. What shape, letter shape does this look like?
Yes.
An S. Sometimes these are called S curves because of that. They're all going to kind of look that way. Okay. And we'll look more at like this cumulative relative frequency idea when we talk about distribution, probability distributions later. So again, the cumulative relative frequency graph is really just the same thing as your cumulative relative frequency. We've just replaced, or your cumulative frequency graph is the same as the cumulative relative frequency. We're just replaced the counts by percentages, right? So if I graph the same thing with the relative frequent or the counts instead, notice that the shape is identical, right? Okay. Another common measure for center is the median. What's the median? From back to pre-algebra. It's the middle number or the midpoint in our distribution. So that we want half the numbers smaller and the other half larger, aka it's the 50th percentile. So if I have a distribution and I want to find that median, I'm going to range all the values from smallest to largest. If the number of observations is odd, the median is just the center. If it's even, then the median is the average of the two center observations. Everybody kind of remember doing that from middle school, probably was when we did this stuff. It was a long time ago. So here's an example. The data below to find the median of the commuting times in minutes of 20 randomly selected New York workers. What am I going to start by doing? Range it in a line. I like stem plots for this. It makes it really easy to count. Okay, so I've done that. There's my key. So I can just kind of count. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9. So this is my middle two values. Everybody agree?
Yeah.
I just like slashing one off on each side is easy. So that represents 05 represents 20 and 25. So the median is going to be the average of those two, or 22 and a half minutes. Cool beans? Okay. Just FYI, the stem plot, not necessary. You could have ordered this just written the numbers in line below it. I like using a stem plot because then I don't have to worry about oh no, I forgot this 15 in here and I have to erase all this stuff after it to put the 15 back in. It's just to me, it's less of a hassle to just use that, but you don't need to. So another thing we'll be interested in when we're looking at percentiles are the quartiles. So to find these quartiles, again, we arrange the observations in increasing order, locate the median. The first quartile, we call Q1, is the median of the observations located to the left of the median. So that means you do not include the median. And the third quartile is the median of the observations located to the right of the median. The percentile rank for these quartiles, Q0 is just the 0th percentile. Q1 is the 25th. Q2, that's the median, is the 50th. Q3 is the 75th. And Q4, shockingly, is the 100th percentile. I know that's really surprising. All right, so here's our cumulative relative frequency graph from before. And what we want to do here is figure out the approximate quartile ranks for the distribution. So at 0%, we are at 40. At 25%, we are maybe 51 or so. At 50%, we look like we are, At 75%, we're probably up here, track down around 60. And then at 100%, we are about 70. Everybody cool on how I did that? Where I just like read the percentages off and then tracked down. It's like graph reading 101, except for starting at the y and reading to the x rather than starting at the x and reading to the y. So here, what do we have? What's different?
Oh, it's not percentage.
Yeah, it's not a percentage. This is a cumulative frequency graph rather than cumulative relative frequency. So if I want the quartile ranks for this, what do I need to do?
Find the median of the.
Oops. So what would the median be, though? Well, that's a great question, right? So what we'd want is we have 44 total presidents, right? So how many presidents should be in each quartile then? Or 11, right? 44 divided by 4 is 11. So 11 should represent like Q1. So if I track like 11 over, if I do Q2, that's like 22. I track 22 over. Notice I'm getting like the same values that I did before. Q3 should be like 33-ish. And then Q4 should be 44. And shockingly, same values, right? That's it for 7.2. Woo!